In this video, we'll discuss how to print all the nodes in a directed graph using a level order traversal. So the immediate clue for this question is that we need to do a level order traversal. And that tells us that we want to use a BFS, a breadth first search, because that allows us to go level by level. You can see the graph, the example graph that we're going to work through here. And we are not just going to start at the 0 node like we did previously. Instead, they are going to give us an input node. So for our example, they're going to give us the 4 node as an input. So this one down here. And our task is to print the entire graph. So I want to start by writing some pseudocode for what our approach is going to look like. And then we'll go through the example and walk through it, diagramming everything out. And then we can see how it works in code. So in terms of the pseudocode, it's going to follow very closely after what we did in the last video. So the very first thing that needs to happen is we need to create our queue and put our first node, the 4 node, inside of it. So let's say the very first thing we do is we want to say create the queue. Let's just say create and fill the queue. You know what? We can just assume that creating the queue is kind of obvious. That's not that difficult to do. But what we want to do is fill the queue with the first node. So let's say with the first node. Then, if you remember, our terminating condition previously was that when the queue is empty, that's when we stop executing code. So what we'll do is just say, we can keep some more space. We can say, while the queue is not empty. So while queue isn't empty. Isn't empty. What do we want to do? And we'll do some stuff inside of here. So what will we do? So if you remember, the way it worked before is we would first pull a node out of the queue. So let's say remove node from the queue. And what are we doing with each node? Well, in this problem, we are just printing all of the nodes. So when we grab out the 4 node, all we want to do is just print it. So let's just say print node. And then, if you remember what we would do in the previous videos, we have to add all of the children to the queue. So that's the next step, is add children to queue. And that is actually all. This is the core of the BFS algorithm, and you'll see this appear over and over again in code. So let's walk through our example here and actually diagram it out. So we get our input, which is the 4 node. We see that on the top left. The first thing we're going to do is fill our queue with the very first node. So we fill it with the 4 node. Then we say, all right, while the queue is not empty, clearly the queue is not empty. So the first thing we're going to do is remove this node from the queue. So we're going to say get rid of 4. We don't want it anymore. We're going to print our 4 node. And then we're going to add the children to the queue. So I have this output over here that just represents whatever we're printing. So we can just grab our 4 node and put it right here because it's going to be printed. And then we add the children of the 4 node to the queue. So what we want to do is we want to say grab the 2 node and the 5 node. So say get 2 and 5 and add them to the queue. Then we go to the next iteration. We say, all right, remove 1 node from the queue. So we pull out this 2 node here, and we're going to do 2 things. We're going to print it and add its children to the queue. So let's print it. We have a 4, now we have a 2. And then we've got to add its children, which are 0 and 1, to the queue. So we say, all right, we come here, we add 0, we add 1. Next we we finish this iteration. Now we go back to the top of here, because we're on the next iteration. So we say, all right, remove the next node from the queue. That's going to be the 5 node. And then we're going to do 2 things. We're going to print it and add its children to the queue. So we come over here and we print it, and then we add its children to the queue. There's only 1 child, which is the 3 node. So let's add that here. Okay, now that finishes this iteration on the 5 node. Now we're going to come here. We're going to say, all right, grab the very next node in the queue, which is our 0 node. We're going to print it over here, and then add its children to the queue. You can see that it doesn't have any children, so we don't have to add anything to the queue. Now we come here, we say, all right, grab the 1 node, pull it out, and we're going to do 2 things. We're going to print this node, and then add its children to the queue. So we print 1, and then we add its children to the queue. But it doesn't have any children, so that's totally fine. We can just move to the next iteration. Now here, we're going to say, all right, grab the 3 node, pull it out of the queue. Print the 3 node. A little bit running out of space here, but it's okay. I can go out of bounds a little bit. We print that node, and we add its children to the queue. Well, 3 doesn't have any children, so we can go ahead and erase these commas. We realize that we've finished this iteration. We go back here, and we check. Is the queue empty? It is empty. So we're done. We were able to, in a level order traversal, print all of the nodes in this graph, starting at the input node that they gave us. So we printed 4, then 2, and then 5, and then 0, 1, 3. And one thing I want to note is, with the exception of this line of pseudocode right here, the rest of this appears all of the time when you're doing a BFS problem. Like almost every single problem will have these same ideas. So if you get really comfortable with the general process of a BFS, really all you change is this line here, which is just representing, hey, what do I do on each node? It's really the only part that changes in a significant way. Okay, so with that being said, I want to briefly go over the time and space complexity. We discussed it in the last video, and it isn't too different here, so I won't spend as much time on it. But we know that we can do this down here. We'll say the time complexity is going to be O of V plus E. And let's go ahead and define our variables. That's always a really good practice. So we can say V is the number of vertices, and E is going to be the number of edges. So our time complexity is O of V plus E. Remember, it's O of V because we're touching every single node in the graph. It's O of E because in total, not at one iteration, but in total, we'll traverse all of the edges in the graph. The space complexity is going to be O of V because in the worst case scenario, we have a graph where there is a single node in the center and everything is connected to it. And in that case, we'll have all of the nodes except for 1 in our queue. So that's O of V minus 1, which is just O of V space. Okay, that's it for the approach. Now we're going to go ahead and jump into the code to see how we can implement this. Now, let's see an example of how to solve this question in JavaScript. To get us started, I have copied our input and output from the example, and I've imported the queue that we will be able to use, the queue class, for our BFS. The input is the 2D array we discussed earlier. It's a directed graph. And then we also have an input node, which is the node that we should start from when we're printing our nodes in level order. And here is the output. It just says, in what order we should be printing our nodes. All right, so let's go ahead and write our test first. So we know we have 2 inputs. The first one is going to be our edges, which we can grab from here. And second, we can say start node is going to be 4. And what we want to do is we just want to invoke our function print nodes in level order, and we'll pass these 2 variables as arguments here. And this function we will write now, but assuming it works, this should be all we need to test with our example. All right, so let's define that function. It's going to take in a bunch of edges and a start node. And then what do we want to do here? Well, the very first thing you want to do whenever you have a graph that comes in this format is you want to convert it to a hash map for the reasons we've discussed before. So in JavaScript, that'll be an object. So let's just say our graph is going to be build graph, and we'll pass edges. So we'll write a function that will build our graph for us. This is a very common function. It looks pretty much the same every single time. The only thing that changes is if you have a directed graph, it looks one way. If you have an undirected graph, it looks a little bit different. But the core idea is the same, and you can use it all the time. So it's very good to get familiar with. So here we're going to have our graph, which will be an object, and we'll return it in the end. Then we're going to iterate over every edge, and we'll say, what do we want to do for each edge? Well, we want to grab the start and the end node out of that edge. So if we're looking at this edge here, right, 4 is the start node and 2 is the end node. So we're saying grab that out using some destructuring. And then all we have to do is say graph at start dot push end, which is saying, in our object, go to the key of 4 and its value will be an array. Add 2 to that array, which basically says, hey, from the 4 node, I can get to the 2 node. The last thing we need to do is we have to actually make sure that there is an array that we can push into. On 26 we're pushing, we have to make sure that that is valid. So what we'll do is we'll just say, hey, if graph at start doesn't already exist, we can just do this. If graph at start is like a falsy value, then what do we want to do? We want to just set it to be an empty array so that when we push on line 26, that'll be totally valid. Okay, so now we have our hash map that we've seen many times before, and we're ready to start actually attacking this question. So we know we are going to be using a queue for our BFS. So let's go ahead and start with that. We'll create our queue here. Now, the first step once you create your queue with a BFS is you will always have to add something to the queue to get you started. So we'll use this onQueue method or enqueue, and we'll put our start node here. So in this case, it's the 4 node, but we don't know that. That's why we are given it as an input, and we can make sure that we are always starting at the correct node with this line here. Okay, now we'll say so long as the size of our queue is greater than 0, which basically means so long as anything is in the queue, we want to continue looping. Now, what do we want to do in our loop? We said there are 3 steps that need to happen. We pull something out of the queue, we process that node, and then we add all of the children or neighbors of that node to the queue. So step 1 is grab a node out of the queue. So let's say node is going to be queue.dequeue. This just says remove something from the queue, and we're storing it in the variable node. Next, we want to process that node. This step really comes down to what do we want to do for every node in the graph. Here, we just want to print every node in the graph. So let's just print the current node. And the idea is this line right here should be run on every single node that is present in our graph. And lastly, we want to say, all right, we've finished processing this node. How do I now add the children of this node to the queue so that we can continue iterating? Well, first of all, we need to grab the children for this node from the queue. So the way we know the children is basically we're asking the question, from my current node, what nodes can we get to? And that's the whole purpose of our graph. That's the whole reason we reformat it, is because we can easily find the answer to that question just by doing graph at node. Now, what we want to say is iterate through our children. So for each child, what do we do? Child. We just want to add that child to the queue. So we can just say queue.enqueue, our child. So just say, hey, add this person to the end of the queue so that they get processed. Or I shouldn't say person, this node. There is one exception here, which is that if this is there could be a case where there is no such thing as graph at node, because that maybe there's like let's find an example of that. If we look at 3 here, there would never be a key of 3 in our hash map, right? Because we only create a value when something is the start node, meaning the index 0 in an edge, and 3 is never index 0 in an edge. So when we're on the 3 node and we try to go to graph at 3, that doesn't work. It'll give us undefined. And then if we try to do undefined.forEach, that'll cause a problem. So we can add a really simple check here that's just saying, hey, if children is falsy, just continue. Just move to the next iteration. Don't even worry about doing this. Because clearly there are no children you need to worry about. But if there are children, you want to add each of them to the queue. Okay, so this is a lot of code. I want to highlight the pieces that are very consistent between problems, because a lot of this stuff you can just use this code on future problems. The code really doesn't change that much when you're doing BFS problems. So this part here, where we build a graph, that again is identical. The only difference is if it's a directed graph, you do it one way. If it's an undirected graph, you do it another way. This part is very standard. You create a queue and you put something inside of it to get started. This condition is always the same. I've never seen it change. This part is very, very standard. This part can change. This part is very, very standard. You have to add the children. Sometimes the way the children are formatted is a little bit different, so the code changes a little bit, but it's not a huge change. Really, it just comes down to get the children, add all of them to the queue. So really, the only thing that is unique about this problem is this line right here on 41. And this is what I call processing the node. So really I have 3 steps. Step 1 is grab a node. Step 2 is process the node. Step 3 is add the children. So this step 2 of processing the node is the part that changes between problems. In some problems, like this one, you'll just want to print that node. But maybe in a different scenario, you want to return something when you find a special node or I don't know, modify the current node or whatever. Really, this part is what you change to modify what you do at each node. In this problem, we're just printing each node, so we just have console.log that node. So I want to be clear that if this does seem intimidating, do understand that once you practice it, almost all of this code can come automatically without much thinking because it is it's repeated across a lot of problems. All right, so we have our test written here. Let's go ahead and run our code to make sure that it works. So we should be getting, let's look at our desired output. We should get 425,013. So let's see. We get 425,013. Okay, fantastic. Now let's talk about the complexity here. So we'll define our variables. We'll say v is the number of vertices, and we'll say e is the number of edges here. So our time complexity is going to be O of v plus e, and our space complexity is going to be O of v. Yeah, okay. So our time complexity is O of v because, the v in our time complexity comes from the fact that we are traversing every node in our graph, which means that every node will be added to the queue at some point in time, and adding a node to the queue happens in constant time. So we are adding v vertices or nodes to the queue. Each one happens in constant time, so that's O of v. Now, for why this O of e is here, you can think about it this way. For every node, we are going through all of its edges, right? We're trying out all of its edges. So if for every node we test for a particular node, we test all of its edges, and we do this for every node, then we are testing all of the edges in the graph. We are traversing all of the edges in the graph. So our time complexity is saying, hey, we depend on v, the number of vertices, because we're adding all of them into our queue, and we depend on e because we're also traversing every single edge in the graph. Oh, I forgot to write here, this is the space complexity. And for the space complexity, well, in the worst case scenario, we could have a total of v minus 1 vertices that sit on the queue at the same time. Because if we have one central node and then every node around it, every other node comes out of that central node, then when we process the central node, we will add every other node in the graph to our queue, which is a total of v minus 1 nodes. And at that point in time, our queue holds v minus 1 different data points or nodes. So we have O of v space in the worst case scenario. All right, that's all for this video, and I'll see you in the next one.